Okay, everybody, I'm sorry, just taking a second to get myself situated here. Okay, cool. All right, so let's pick up where we left off. We're gonna kind of, I think we've had some introduction to this line of thinking about what we chose color and flavor for electron, and these are binary properties of the electron, in the sense that there's only two options, right? And the point of this exercise that we've had in problem set one is not really to get you to necessarily understand the underlying principles of what's going on, but rather just to work with the math and kind of get a sense of the kind of logic, internal logic we need to have to analyze these problems. So what I'm going to do today is kind of finally formalize those underlying principles to this issue of color of the electron. And we have to kind of generalize things a bit more because there's going to be properties that we want to measure that aren't just binary. Right? The thing about color that's really nice is there's only two options. Right? It can either be white or black, totally independent of anything else. You only have two options. But imagine instead we have a box or some sort of detector that every time an electron passes by that detector in position, it clicks. Right, so think that you have like a box and each there's little points across that box with a little detector. And every time an electron passes that little point in the box, the detector kicks off, right? So you're measuring the position of the electron as it's moving through the box. The thing about position is that it's not a binary property, right? It's not that a box has two positions to choose from. It's that the box may have infinite number of positions to choose from, right? We take the distance from, we put the box to be the size of the room. We can subdivide the length of the room any way we like. We could just do like at every crack, we could put a detector, right? Every crack, we could put a detector, and there would be something like 30 detectors along the line. And we would want to come up with a representation of our electron and the probabilities of observing that position of where the electron is by measuring at each of those 30 detectors. Right? So what would the vector for that look like? Well, the vector for color is two components because there are unique probabilities to detect either white or black. Right? So the length is 2. If we have 30 detectors of position, the vector for that electron is going to be 30 elements long. So the elements of the vector are the probabilities, or related to the probabilities of seeing that electron at each point. Right? And so it's going to be a 30 component vector, and our detector box will be a matrix that's 30 by 30. Okay? And we could come up with that. It's not hard. There's a formalism that we'll come up with that allows us to write that down. But as you can imagine, that's not convenient. And again, most boxes, we're not going to be looking at boxes or areas that are neatly discretized into 30 little chunks. We're going to think about an electron that can exist along any point in this room, right? And that's going to be an infinite number of spaces. Right? There's an infinite number of points between that point and that point. If you guys don't know this, it's really, really interesting. No, let's ignore that. That's a fact that's not relevant here. I mean, it'll come up in a second. But you can imagine, right? I can choose any kind of lattice spacing, the spacing between my detectors I choose, and that spacing can be infinitely small. I can have a fully continuous detector. And what would the vector for that look like? Well, it would be infinitely long, and the matrix would be infinitely large. Right? And we don't want to do that, right? But that's not very helpful for us, and that's a bad way to tackle the math because we don't want to deal with infinities. So we're going to have to think of a different way to represent the system in terms of instead of matrices and vectors. Right? Because we're going to have systems where we want to measure something where that property is continuous. It's an infinite number of values. So matrices and vectors won't work very well. What we'll find is that we can interchange between these two kind of approaches. So what we're going to do instead is instead of thinking of the electron wave function, the psi for the electron, as a vector, we're going to think of it as a function instead. A function that's defined on every point in our box. Okay, and then we'll have to think a little bit about, well, if the wave function, this vector that represents the electron is now a function that has a point along every point in the box, what is the vector, or what is the matrix in this discussion, right? Because we can't work with an infinitely sized matrix. I'm never going to make you guys do infinite multiplications, infinite dot products. So there must be a way to kind of transform this matrix and vector approach into something that's continuous, something that's defined at every point in space. And we're going to find that that'd be very useful for a lot of the analysis in this course. When we're going to think about the hydrogen atom, for instance, the hydrogen atom has an electron that's, I'm going to put in quotations, orbiting a proton. And it orbits in a sphere effectively. Effectively, it's spherically symmetric, so it can orbit in around the sphere surrounding the proton. And there's going to be infinite number of angles that the electron could be at, right? The electron can be here relative to the proton, which is my giant head. It can be over here, it can be here, right? It can smoothly vary around the axis of the proton. And so the wave function for the electron from the perspective of its position around a proton is going to have infinite number of values. It's going to have an infinite number of values. So we have to come up with some functional way to describe things. And so we're going to find that using functions instead of vectors will be very convenient for some problems. But when we talk about problems that are discrete, like color, there's only two options, not an infinite number of options for that electron. It doesn't make a lot of sense to think about functions, right? Because it's only two outputs, two values. Right? If there's a small number of values, it makes sense to take with matrices and vectors. But we're going to want to think about position and other things. We're going to use functions. Right? We'll talk about that in math today. And so what we're going to discuss today, we'll take some time. And I think this will be kind of a 2-day process. Trying to give you guys lots of examples as we go through these. Right? And what we're going to learn today, start with, is the underpinning of this quantum mechanics, microscopic physics of molecules and atoms. Like just like in intro physics, you learn Newton's laws. And in thermo last semester, we learned the laws of thermodynamics. We have a set of laws for quantum mechanics, things that all systems have to satisfy. And the interesting thing about, as we'll see, in quantum mechanics, the criteria that, say, a particle has to satisfy in order for it to be valid, a valid representation of a physical system, is very, very stringent, very limited. Compared to Newton's laws. Newton's laws say you can stick any old billiard ball you want, any funky shape, and make it go flying in any direction and make that chaotic and making it jump back and forth and do crazy stuff. And Newton's laws have no problem with that. Quantum mechanics will not let you do that, right? Quantum mechanics only allows a certain type of physics, if you will, for that particle. There's a very specific prescription for how a microscopic particle will function, and there's not a lot of variety. So in some ways, it's a very limiting theory. It's not nearly as open and freely moving as Newton's laws, right? So that limits the number of things that we can talk about, and it also makes things a little easier. Now, that doesn't say that the things that we use to apply to analyze these problems are easy. They're hard, but there's far fewer wiggle room and flexibility in the theory. Okay? Things are kind of much more rigid, and we'll see that today. All right, so what we're going to learn today are not the laws. We'll have to talk about what the difference between a law and something else is, but if it's relevant, you can certainly ask that. But today we're going to start discussing what are called the postulates of quantum mechanics. And you may wonder why they're called postulates and not laws. A postulate is something we assume to be true. Right? So this is an interpretation of microscopic physics, microscopic chemistry or physics, that we assume to be true. All right, so we're going to make a claim that these statements are true. And what will disprove us, of course, is experiment. And we've had a century of experiments and all of these things are true, right? So they're not really laws because it turns out there's different ways to interpret quantum mechanics. There's different frameworks, if you will, for thinking about things. For instance, we've been talking about this idea, right, of white and black electrons. And it almost feels like sometimes, and you'll see this on the homework, like it's like if you send a white electron one way and a black electron the other way, or vice versa, once one person measures one, they know exactly what the other one is. And that seems to be counterintuitive, as if the person who detects it knows some information about an electron that's miles and miles away before anyone else does. It seems like information travels faster than light. And that's part of the interpretation that we pick. But there's other types of ways to interpret that. For instance, there's what's called the many worlds interpretation, which is the idea that each of the possible pathways for this electron, whether black or white, are different universes, and the system has to eventually probabilistically chooses one of the universes. And so we're constantly evolving, our universe is constantly evolving from one state to another state, and every time quantum mechanics needs to make a decision between black and white, it's what's in the two paths, right? And that resolves some of this, as Caitlin said in an email to me, the Schrodinger cat kind of problem, right? That the cat is both alive and dead. The idea is that the many worlds interpretation of this is that there are two pathways from current time, two different universes, one where the cat's alive and cat's dead, and time splits off that way, and you as the observer ends up being in one of those timelines. Okay, that doesn't mean the other timeline doesn't exist or not. You don't know, you can't observe it. But that's how it works. That's how the many worlds interpretation works. That instead of time being linear, time is constantly branching off instead. And some people are a big believer of this stuff. I find it to be very hard to do experiments from that point of view. Okay, so one of the useful things about this interpretation that we pick is that it's very easy to do experiments with it. We don't have to think about universe stuff. Okay, so it's much easier to do the math, the calculations, and understand the physical behavior of molecules and atoms if we use this kind of traditional approach, not this multi-worlds, many worlds approach. All right, and I'm sure you guys have heard of these things, and of course, Marvel is very famous for using the many worlds approach to things, and they do a fairly poor job of it. But that's the way it goes. So, Big Bang Theory does a far worse job, so to be fair. So let's talk about these postulates. And so this interpretation it has a special name. And in fact, there's a famous play about this interpretation called Copenhagen. It's called the Copenhagen interpretation. And it's named this because, and I'll find a picture of it, because a bunch of chemists, or not a bunch of chemists, a bunch of scientists came together in 1927. I think it's 1927. Copenhagen meeting. Copenhagen interpretation. Yeah, 1927. There's a big conference of all the famous physicists in the world that come together in 1927 to decide on this new quantum mechanics and what they think about it. And so this is a picture of everyone who visited the Seoul Day Conference in 1927. Again, I don't expect everyone to know who these people are, but you can see Einstein's right smack in the middle. Niels Bohr is in here somewhere. We'll mention many of these people throughout this class. Basically, every famous physicist from the turn of the century is in this picture. It's one of the most famous or infamous people. This is Erwin Schrodinger. We're going to talk about him today. Where's Niels Bohr? It's hard to see here. Anyway, we'll talk about these people and I'll try to mention them. And so they came together to try to figure out this theory, and they came up with this interpretation. They kind of all agreed in consensus this is the best way to talk about these things. And it was done in Copenhagen in 1927. So this is, again, some of these things are arbitrary. It's because we're doing interpretations, we're detecting things that are statistical, probabilities, 50-50, things like that. So there's always some uncertainty or ambiguity in how you interpret these things. And we'll see that as we go through the class. Thankfully, it's not too bad for us chemists. We'll find a lot of things are very certain. right? So there's about 5 or 6 different postulates, and we'll kind of go through them slowly just so we can understand them. And the big one that we're going to start with, let me pull it up, sorry. It's postulate 1. And this is what's called the wave function postulate. The wave function. Right? So a state of a microscopic system, a quantum mechanical system. Well, again, we haven't quite defined what microscopic is yet, but we will. But you can think of like an atom, molecule, something very, very small, on the size of an atom, is completely specified by its so-called wave function. Okay. And the label that we use for wave functions, we've already seen last class, which is a function. Right? We call it psi. Anytime you see this label psi, think the wave function. This is something that's representing an electron or an atom or a molecule. We'll also see that it may represent a state or an orbital of an atom, for instance, like the 1s orbital has a wave function and so on. So we'll look at all of that. But anything that's quantum mechanical and exists will have a wave function that describes it. And it describes everything. So if you know the wave function of your object, right, however you measure it, however you calculate it, right, there's lots of different ways to do that. Depends on the system, of course. If you know that wave function, you know everything about the system. All right, everything is determined, properties, evolution, its existence, you name it, is defined by its wave function. Okay, it's an object, a mathematical object that completely describes the system. And it's a function of position, which I'll write R. And I'll tell you what, I'll make a note what that is. Position and time. Right, where R, again, R is position. Right, it's like a vector X, Y, Z. Right, it's a position in space. The position vector, I'll write that, position vector. All right, so again, the idea is that, for instance, if we have an electron in this room, it has a wave function, and that wave function at every position in the room has a unique value. And if we know all of those values, we know everything about the electron in our room. And it may change a little bit as a function of time. We'll see that. We'll see why we have to include time. And of course, that would be meaningful to include time, right? Because we may drop an electron right here, and we want to know when it ends up on the other side, right? So we need to think about time, right? Just like a billiard ball. All right, you've seen these wave functions. Again, the wave functions are like the black and white, right? The 2 component vectors that we looked at for black and white electrons. That's the wave function of the electron from the perspective of color. Here, the input of that wave function is the color, not the position. Right? That would be wave function. It would be psi of color, and that would give you some information about the system, depending on its value of its color. So it's just some property. All right, let's name a few. Let me make a few properties of this wave function that are really important. First of all, properties. All right, all wave functions have to satisfy these properties. All right, one is that the wave function psi may or may not. It turns out to be our choice, but we're going to have to consider it, may be complex value. What does that mean? Well, that means that what that means is that there might be that psi of R at some t might look like a imaginary number, a plus bi, where I is equal to the square root of -1, right? There might even be some i's inside the function, okay? It may be complex value, right? We're going to try our best to stay away from complex numbers in this class, all right? But as we'll see in the next week or so, you can't get rid of them. Real life is complex, right? It's kind of the crazy thing. That's why I don't like calling them imaginary numbers, because they're not imaginary. Real physics, the real physics of the universe requires the existence of complex numbers, okay? We'll talk about why that is, right? So don't be too scared by complex numbers. We'll talk about why you need complex numbers to describe the world. And we'll also show that you can make choices to get rid of them as well. Okay, so if we want to talk about a representation of our system that doesn't have any complex numbers, we can do that. And in fact, you saw that, right? We didn't deal with any i's at all, the color and flavor, right? You didn't see a single I. But there is a way to do that exact problem with complex numbers. Okay. And it actually, if you use it with complex numbers, it changes the answers on 1.6 and 1.7. If you include complex numbers, the results are actually a little different. So we get some trade-off sometimes if we choose real numbers instead of complex. And we'll look at that while we're here. So don't worry about it too much right now. Just remember in the back of your mind that I may show up somewhere. Right? We'll have to think about what physically does I mean. And we won't be that. We're not that far from thinking about that. I'm going to go to the next page. All right, so the second property is that because it may be complex, and let me change it. Sorry, I should be more specific. Because psi may be complex, there exists a so-called complex conjugate of psi, which we label either, there's two different labels I'll use throughout the class. Sometimes I get lazy and I swap. One, I'll put a little, what's called a dagger, looks like a cross, or I'll star it. I'll put a star up there. So anytime you see psi star, I'll sometimes even call it psi star or psi cross. Right, these are what are called the complex conjugate of the function, and a complex conjugate is very easy to understand. To calculate, it's just where all i's are multiplied by -1. Oh, sorry, by -1. All right, so let me give you an example. Imagine that, so here's an example. If psi is equal to some number a, e to the I x, right? So where x is the position, right? So this is psi of x, e to the I x. We'll actually look at this function very soon, e to the I. You probably never, maybe you've never seen that, e raised to an imaginary power. It's a very interesting function. But the complex conjugate of this is very easy to calculate. All you do is add a negative to the I. So psi star or psi dagger, whatever you prefer, of x is a to the -ix, right? You just take every I and flip the sign, okay? Super easy, all right? We're going to see complex conjugates all the time in this class, and I'll show you why in just a second, all right? Now, if it's a real function, if it's a e to the x, then a complex conjugate is exactly the same, okay? Because there's no i's, right? You don't do anything if it's real, right? If the function is real, so I'll just write that here. All right, that is a terrible piece of writing. Sorry. So if psi is real, psi dagger is equal to psi. Okay. And we're going to look at a lot of systems where we don't have i's. So whenever I say psi star, you just think we're going to We're just gonna fix that. This has a nice property. Right? And we'll see that in just a second, right? So the important the next property is where this complex conjugate comes into play. Number 3. The wave function when squared. Oh, sorry, let me change that, not squared. Let me start over. When multiplied by its complex conjugate, so that would look something like psi star of x times psi of x is always real. And I'll prove that to you in just a second. And represents the probability of observing the system or the particle, the system, we'll just say the system, it could be electron or whatever, at position X. Okay, so what that means is, so like for instance, imagine I have in my room, all right, so here's my little box. All right, here's my box. It has, and I'm going to make it a cube or just like a 3D rectangle just to be helpful. All right, that's not the best box in the world, but that's okay. And let's say it has length X, Y, and depth Z. Okay. And I have one electron in this box, and I want to ask the probability. I want to ask my system, what's the probability the electron is in a little point, like a little cube, little section of my box, right? So let's mark out a little section of the box like this. So there's my little section of the box, and it has size dx, dy, dz. So the volume of this box is the volume of this little box. So I'll do V green box is dx, dy, dz. That's the volume of that little box. And the probability of the electron in this box is equal to psi star psi dx, dy, dz. Okay, so anytime we want to calculate a probability, we need to take a square of the wave function. So if this was a real function, this is psi squared, right? Because it's psi theta psi. So you can kind of think of this as the square, right? If this is complex, we got to make sure to flip the i's around. All right, and let me show you why that is. All right, so if this is real, it's psi squared. I'll just write that here. If we choose psi to be real, then the probability is psi squared. That doesn't look like a psi, that looks like a swastika. I'm sorry. I don't want to go all Elon on us today. Psi squared dx dy dz. All right, so sorry, that's what we got to do. So the interesting thing, and so what this means is that, remember, well, all we measured with the electron is its probability, right? We said something, all we could really say about the electron is that there's a probability of it being white when we detect it or black, right? And that's what those coefficients on that vector were. They were the probabilities. And so when it comes to wave functions, what that probability is the square of the wave function. So what we actually measure in the lab are properties of the square of the wave function. All right, so the psi squared is what we call the probability density. It tells me at every position in the box, what's the probability of observing the electron there. Right, and that turns out that's all I can say about the electron is the probability. Just like all I can say about the colored electron is the probability that it's white or black. And so by measuring psi squared, this tells us exactly what the probability is to find the electron. Okay, and so that's what we actually measure in lab because we've got little a matrix of detectors in our box. And we know the electron is bouncing around for some amount of time, and we measure all the numbers of clicks for all the detectors. We divide that by the number of seconds we measure, and that tells us roughly how many times it clicks per second in this box, and that gives us a sense of its probability in the box. Right? And that comes from psi squared. All right, so the wave function is this object, it's this representation of the molecule that we could write down, and we will write it down, but it's not really a measurable thing. Okay, it's like an object that encodes the information of the molecule or the system, but what we actually measure is its square. Okay, we'll see that plenty in this class. Anytime we're going to do a measurement, anytime we're going to start thinking of something, we're going to start multiplying psi by itself because that's what we actually measure. Right, we'll see that, I think, today. See how we use that. All right, so now I'm going to stop for just a second and let's just look very briefly at why these are equivalent and why I want to multiply by the complex conjugate instead of just taking the square of a complex function. Right? Imagine psi is complex. Why do I have to take its conjugate? Why can't I just square it like I do a real function? That's really easy to show. All right, so why complex conjugate? All right, so I'm going to show you. I'm going to teach you just a little math trick. All right, we saw that crazy function e to the ix, and that seems like a really weird function. But let's use it and play around with it a little bit. All right, so let's assume the wave function representing our electron in a one-dimensional box. All right, so it's just on a line. Right, it's just moving back and forth. And the box is infinitely large. It's just kind of floating around. And we'll just say it as a function of time as well. Is equal to, let me get rid of the time dependence, actually. Let's just do position for now. We're just going to freeze it in time, okay? Is A, which is some number, e to the I kx, where x is position. It's a variable. K is just a number, right? And A is just a number. Yeah, go ahead.
So when do you use x and when do you use it like in its vector form? You're saying like R is like vector.
It depends if you're what dimension you're in. So if this is a three-dimensional box, we would use x, y, z. Yeah. So R in this case is a one-component vector that's just x. It just depends on the box. I'm just keeping things simple here. All right. So here's an interesting fact. And this is something that we'll use quite a few times in this class. And it's really, really helpful to start understanding, because we're going to see this function a lot or a couple of times. And it's like, what the hell is e to the I? Well, there's a beautiful formula that Leonard Euler derived 500 years ago, almost 500 years ago now. It's called Euler's formula. And Euler shows that e to the ix, well, let me add the k just to be safe, is cosine kx plus I sine kx. Has anyone ever seen that before? Have anyone ever seen this formula before? Maybe not. Might be not something you ever consider. This is one of the most beautiful formulas in it's math. And the reason why it's beautiful is that if you take e to the I pi, right, three important numbers, this is equal to cosine pi plus I sine pi. The cosine of pi is -1. The sine of pi is 0. So you have e to the I pi is equal to -1, right? All four of the three of the most important numbers in math all together in one beautiful formula. It's pretty cool. I guess it is. So this is a really useful one to remember. And the thing about this, like, so what is cosine plus I sine kx? This is motion on a circle. Let me show you that. This is motion on a circle. All right, so we're going to plot this like a complex number. So we're going to put the real part of the complex number, and that is, this is the real part, and the imaginary part is the part with the I. We'll call that IM. All right, so we're going to plot the imaginary part of the number on the y-axis and the real part, the cosine part, on the x-axis as a function of x. Okay, so let's go ahead and put 0 in there. If cosine is 0, if x is 0, then cosine of 0 is 1. Sine is 0, so this number is 1 on the real axis. This is x equals 0. All right, let's go to x equals pi over 2. All right, x equals pi over 2 is cosine, let's say k is 1 here. Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so that's I, or 1 times I. So this is at 1 at x equals pi over 2. And not surprisingly, as you continue, that it just goes around the circle, right? I don't need to keep showing this to you. But these coordinates, this e to the I pi, e to the ix, that's a terrible circle, excuse me. Let me draw a real circle. That's not good either. I want it to be about the same size. All right, good enough. Let me erase this thing on the inside. All right, so e to the I pi, or e to the ix, rather, is just circular motion, right? It goes, let me clean this up like this, right? E to the I pi is circular motion in the counterclockwise direction. So this is e to the ix. Right, so when we have something that looks like e to the I, think something moving in a circle. Okay, it's moving in a circle. Now it's moving in this weird complex space, and we don't really quite know what that is. There is a physical interpretation of that from electromagnetism, because the electric field, electromagnetic wave, also has a complex motion like this. It's why we have a magnetic field. Why there's always a magnetic field of the electric field perpendicular to it is a part of the complex nature of the electromagnetic field. And so we have some object, right? What it's like is that this system is like something that's oscillating around in a circle. Like this. Okay. Right, so there's some oscillatory motion to this, right? Something that's moving like a sine wave. Right, but it has to be complex, right? And a couple postulates will understand why this needs to be complex. You may ask, well, why can't we just write it like cosine? E to the ikx is basically proportional to cosine. Why can't we just choose the cosine term and get rid of the I? That doesn't give you the right result, as we'll see in a little bit. Okay, so just keep that in mind. We'll see this e to the I every once in a while. And whenever you see it, just think circle. Think motion on a circle. Something that's going like crewing phase over 2 pi radians, moving in a circle like this. Okay, some sort of wave oscillatory motion. All right, so anyway, let's go back to where we were. So again, the question, of course, is why do we need the complex conjugate? Well, let's calculate, just for giggles, let's calculate psi times psi. Right? Well, that would be a squared, and the a's cancel times, and then be a to the ikx times e to the ikx, right? Which is a squared e to the 2 ikx. Okay, so when we square this function, right, just typically, we still have this complex behavior, right? We just basically just made it go twice as fast. It's twice the frequency now. Instead of going like this, it's now going like this. All right, so that's not very helpful, right? Again, remember, we can't measure complex things, right? Things can move in a complex way, but we only measure the real part of it. We can't measure the complex part. We can measure something moving in a complex way, but we can only measure basically along this axis right here, like along the real axis. So let's try it with the complex conjugate instead. All right, so now if I take psi star of x times psi of x, again, we get an a squared from multiplying the two coefficients, but the first psi is a negative sign on the e. So instead, we have e to the minus ikx times e to the ikx, right? And these cancel out. It just goes to 1. So this is left to a squared, a real number. Okay, that's something we can make real number. Okay? So why we do this is, again, we have some object, and when something's complex, what that means is that it's rotating in a circle, right? In this kind of weird way, right? It has this oscillatory behavior that we represent with complex numbers, right? And e to the ikx is this counterclockwise motion, right? Well, we can't measure, again, this motion ourselves. So when we look at the system, we don't know if it's moving clockwise or counterclockwise. All right, we can't tell the difference. They're equivalent. E to the ikx is a counterclockwise motion. Right? So you have a wave that's moving, the phase of the wave is moving in this direction. E to the minus ikx goes the opposite direction. So what you're doing is you're multiplying a wave that's going like this by the equivalent wave that's going like this. And they cancel each other out. Okay? So we cancel basically by taking psi star psi, we cancel out that ambiguity that we have about the complex numbers, whether it's going this way or going this way as wave. Different types of phases. Basically, the idea is that one of them is the wave is propagating in this direction, the phase is going up and down like this, and the other direction is going backwards. Okay, and so when you have one object going forwards in times like this, and the other one equivalently going backwards in time at the same rate, and you multiply them together, they just cancel out. Destructive interference. And so all you're left with is this real number A. So what does that say? So we'll have to think about what a squared means. But it's a real number. It's something that we can measure. Anytime we get a real number out, it's something that we can put on our experiment, measure with an experiment. All right, so this is why we need complex conjugates. Because anytime, the conclusion is if you multiply a complex function by its complex conjugate, the result is always real. Okay. It's always real. So you always can guarantee that you get a real answer. I'll just write that here. And of course, real means measurable. That's something that we can look at in more. Any questions? One more property that I want to mention now. So again, remember that these wave functions, these are functional forms of these vectors that we looked at. there was another property in the vector that we haven't used yet, which is at the length 1. Right, remember that the vectors can't be any longer than length 1. Right, white is 1, 0, and black is 0, 1. And then black plus white is 1, 1, but you have to multiply by that 1 over the square root of 2 to make it length 1. It has to be a unit vector. Right, so there is an equivalent constraint for these functions. Equivalent constraint. And I'll just write it here at the, let me do it on the next page. Let me do it on the next page. So again, let me just remind you that psi star psi is what's called the probability density and which tells you the probability of observing the system in some state. Right, that state could be called black or white. It could be x equals 0 or x equals 1. That side of this side of the room, in my mouth, on Mars, anything we want, right? We could just plug in the position and it'll tell us. All right, and so therefore, there's one important constraint. Right, the one important constraint is that if the probability, when I got my box that I drew, and then I looked at the probability in one little small subsection of it, right, it's some number, right? I may have a 0.1% chance of seeing an electron in that box. Now, what I'm going to do is I'm going to subdivide the entire big box with these little boxes and add them all up. What should be the probability that I observed that electron in any part of the box? What number should it be? 1. So the total probability density, once we add up all the probabilities of all the little boxes, should be 1. Right? So we're taking these little infinitesimally small boxes and we're summing them up over all directions. That's an integral. It's an integral. So the important constraint is that the integral over the box of psi star psi times the, let's say for instance, dx, dy, dz in 3 dimensions has to equal 1. Right? This is the same thing, right? This is equivalent to vectors of psi must be unit length. It's the same concept, right? When we have a basis or a set of detectors that are discrete, black, white, a set of states that are finite, we said that the vectors had to be length 1. And so the position is infinite and continuous. There's infinite number of places. So we have to use an integral instead. And what it says is that the integral of psi squared has to be 1. Right? It's the exact same statement. Right? We're just doing an integral and using functions instead of using vectors. All right, so this is what's called normalization. Right, so anytime I say that this is what's called normalization, and these wave functions, we say that psi is normalized. Psi is normalized. Okay. It just means it integrates to 1. The square of it integrates to 1. And this is true for every system of a wave function. It's in fact, it's how we construct wave functions. We're going to come up with guesses and we're going to come up with a model for a system and make a guess for the wave function. And part of the process of determining what the wave function is that we have to normalize it with this condition. The square of it has to integrate to 1. If it doesn't integrate to 1, There's no way to take the square of this function and divide it by some numbers to get the integral to be one. It's not a wave function. It cannot be one. So if this integral diverges, say goes to infinity, then that's not a real system. It has to be convergent. All right, it has to be normalized to one. This is one of the hardest rules in physics and chemistry. Okay. So that's the wave function. Right? We're not quite able to construct a wave function yet because we need to figure out all the little tools to help us construct it, which is kind of our next journey. All right, so let's go back and think just briefly about the little mechanics of our electron problem from homework 1. Right? So we've discussed the electron itself. It's this wave function. Right? It's still got some more properties we have to define. But we have an idea that this wave function is some function. It could be a vector. It may be complex. It has some certain normalization properties. It may be oscillatory, right? And complex. May not be. May just be two numbers. Who knows? But we've missed the other half. We need to finish the other half of the experiment, which are the boxes, the measurement devices themselves. Right? The color and the flavor boxes. Right? And we saw that in the matrix, the vector form, that these are matrices. The color is the matrix, the 2x2 matrix, and flavor is a 2x2 matrix. But what is one of these boxes if the thing it's measuring is continuous, like position? Right? Remember, we went to these integral forms, right? So what is the box equivalent to one of the box functions? And this introduces the other major component in this theory, which are what are called postulate 2, what are called linear operators, which is a really, really fancy word for an object that takes in a function and spits out another one with some properties. Linear operators. All right, so for every observable property or measurable property, whichever you prefer term-wise, there corresponds a so-called linear operator. All right, that's not a very helpful definition, I understand. So let's try to understand what an operator is, okay? All right, so a definition. An operator, you can think of it as a function or an object. I like to think of it as an object, a mathematical object. Mathematical object that maps a set of functions or numbers to another. Let me talk about the simplest operator that you know. All right? Define. So here's an example. Define the plus operator. I'll put a little hat on top of it to define an operator. As an object that maps two numbers to their sum. All right, so let's do an example. What's plus operated on 1 and 1? 2. Yeah, okay. All right, we're masters at operators already, right? Right. For instance, right? Plus is an operator. Right? Times is an operator. The derivative is an operator, as we see, right? You take a derivative, right? What does a derivative do? You plug in a function to the derivative, and it spits out a new function, right? Think about, let's go back to our matrices, right? We can already maybe start to see that, right? An operator is something that takes in a function or numbers, some set of numbers, and spits out a number. Right? Let's try another one. Let's think about the derivative function. The derivative operator. Example 2. Derivative. Right? We'll call the derivative the operator d by dx operator, the d by dx operator. And how does d by dx work? Well, it takes in a function f of x and gives you the derivative of that function. Right? So for example, d by dx of x squared gives you 2x. Right? Totally reasonable operator. Right? And so everything that we want to observe about our system, its position, its momentum, its color, its spin, its energy, all we can write down an operator that when we plug in the wave function, it will give us the value of that wave function's property. Right? Just like our matrices, right? Go back to our matrices, right? What did the matrix do in the color problem? It takes a color and you apply the vector to that matrix operator, and it either spits out spits out the same vector again, right? White into the color goes out white times a number. But there are operators like flavor. When you put a white electron into flavor, it flips it into black, mixes it up. So sometimes operators will conserve the function, the same function that goes in goes out, but some operators will change the function as well. Right? The matrix is an operator. It takes in a vector and transforms it into a new vector. So a matrix is a linear operator that transforms one vector into another. Okay. And all right, so there's all sorts of different operators. But the important thing is that, and let me just highlight it like 10 more times, is that it has to be linear. All right, we have to define what that means. So not all operators are linear. All right, we'll see. We'll give you some examples. All right, so let's think about what linear. And this is one of the most unique parts about quantum mechanics is that we'll see what linearity means. Quantum mechanics is what we call linear theory. What that means is if you know the physics of one body, all right, so imagine you have one electron in your box. Okay, 15 minutes. Imagine you have one electron in your box and you measure the wave function. Okay, you know everything you know about that electron, done to death. And now your homie comes in and drops another electron in there. All right, so imagine that these were classical particles, right? They're like Newton's billiard balls. All right, what does Newton say? Well, Newton says, okay, you know exactly how one billiard ball moves around. That's no problem, right? That's what you do in the class. If you have two billiard balls floating around, I imagine they're floating around. They have stable orbits, right? Two bodies have stable orbits. You can solve for that stable orbit, right? So if you know the physics of one and you bring in another one, you know the physics of two. What happens when you put three billiard balls in that box floating around? Do we know the answer to that problem? Does anyone remember from physics? Can we solve a three-body problem? Does anyone know? Can't. Anyone ever read the sci-fi novel Three-Body Problem before? The Chinese novel. It's a very famous Chinese sci-fi novel. There's a Netflix adaptation on it. And it's about, it's got a crazy story, but it's about a virtual reality game where everyone has to try to figure out how to solve the three-body problem. Because you can't, so when you have two bodies, say you have a moon and an earth, you can always solve for the motion of those two, right? With the center of mass approximation, you take a center of mass, it's like you have two bodies on a barbell, like two balls on a barbell, and they rotate around each other. You can calculate the momentum, you get ellipses for rotation and things like that, right? So you learn all of Kepler's laws and things like that for two bodies. Newton knew this. The moment you bring in a third body, you can't solve the problem anymore. The three-body problem is unsolvable. In fact, there's only, of all the possible ways to arrange three bodies that can orbit each other through gravity, the possible trajectories of that are stable in the sense that all three bodies stay in orbit with each other and orbit stably for a long time are minuscule, almost impossible. I don't know what the density of stable solutions are, but it's tiny. Most solutions of a three-body problem, they bring three bodies into orbit, they go flying off from each other. Not stable at all. And you can't solve it exactly. What that means is that the theory of physics, Newton's laws, are not linear, which means that the physics of one body doesn't extrapolate to two bodies or three bodies or four bodies. So physics becomes classical physics becomes very, very difficult the moment you have more than at least three billiard balls. Two is about the best you can do. Right? And you can't assume that the physics of two can extrapolate to the physics of three. It does not, by definition. In quantum mechanics, it does. The physics of one electron is the same as physics of two electrons, which is the physics of three electrons, with the physics of four electrons. So it's basically all you do is you have one electron that acts the same. Now you have two electrons that act the same. They have the same physics. They all interact perfectly fine. You just add each electron to each other. And the physics of one works for all of them. Right? So it's a linear theory, which means that we don't have that three-body problem. We can create a system of 1 million electrons, and if we have the time and the computational power, we can track every single one and know exactly what the total wave function of the system looks like. You can't do that in Newton's laws. Possible. So this is what I mean by linear. So let me just show you what that means mathematically. And it's very simple. A linear operator, and of course linear is satisfies this property of, again, this is a bit circular, linearity. So let A hat be an arbitrary measurement box or an operator such that A, say, imagine applied measuring electron 1, right? So this is our A measuring box. We're measuring property A. And this is electron 1. Okay. And when you apply this, you get a number back, A sub 1, times the original vector, right? Just like we did with color, right? When you feed in a white electron into the color box, you get the white electron out times the number, which is 1. So A1 would be 1 here. Right? So this is this satisfies what I call in the problem set the quantum measurement theorem. This is a proper measurement. And let A on another electron also be satisfied. So you have A2, some number, times psi 2. Let me do psi 1 and psi 2. Then A applied to a combination of psi 1 and psi 2, right? Imagine psi 1 is white, psi 2 is black, A2 is -1, A1 is +1, just like in the homework. Then A applied to the combination of them, C1 psi 1 plus C2 psi 2, right? Like a white plus black electron, is equal to C1 A applied to psi 1 plus C2 A applied to psi 2, which is just by definition C1 A1 psi 1 plus C2 A2 psi 2. All right, so what that means is that this is what I mean by linearity. If the operator satisfies the measurement theorem, or what I called it, the measurement theorem for one thing, and it satisfies it for another object, then it satisfies for the sum of the objects. Right? Physics don't work, Newton's laws don't work like this. Right? If you have a trajectory for one particle, imagine you have three particles here. You have a trajectory for one particle that satisfies F equals ma. You have another particle that satisfies F equals ma. And a third particle that satisfies F equals ma for that, the Newton's laws. Then the sum of those three particles together do not satisfy F equals ma. Right? It's not too hard to show that. Right? So this never applies. Right? If you can solve the problem for three particles individually in Newtonian laws, you can't solve it for all three together. But in quantum mechanics, there's no problem with that. Quantum mechanics says if you can solve it for two, you can solve it for both of them simultaneously. Right? So what does that mean? Well, that means, again, my electron can be white, it can be black, but it can also be white plus black, or white minus black. If I make an ion minus. Right? So it satisfies this linearity. Right? That everything kind of adds up together, right? So this is a really, really, really powerful technique. Really, really powerful discuss our kind of opportunity that we get, because we don't have to worry. If we know how to solve one problem, we can solve all of them. It's really, really nice.
I have a question.
Yeah, go ahead.
Actually, two questions.
Sure.
First, why is like the C, like why are you able to add that constant when you're adding them together?
Well, remember that in, let's look at it like this. Let's do a different example. So again, let's go back to our matrices. So let the C operator be the color operator, which is 1, 0, 0, minus 1. Right? So what is C hat on 1, 0? What is it? I'm asking you,
Oh,
what do we get out?
1,
1 times.
0. Wait, oh, you're saying, oh.
Yeah, what's the color box operator? We get a 1 times what do we get else do we get out?
1 on top, right?
And 0, right? Right, so the vector doesn't change. And let's just quickly do this. What's the result of this?
0, 1.
Times,
Thank you.
right? Minus 1. Okay, so now what is C applied to 1 over the square root of 2? 1, 1.
So,
Which is 1 over, exactly. 1 over, wow, there's a minus sign, right? Which is 1 over the square root of 2, 1, 0, plus 1 over the square root of 2, 1, 1, or sorry, 0, 1, right? You agree with that so far? C applied to that. Do you see how this math works now, right? This is 1 over the square root of 2 is just a number. C applied to 1, 0, plus 1 over the square root of 2, C applied to 0, 1, which is just 1 over the square root of 2, 1 minus 1.
well, why would you take out the 1 over 2? Like, why would you just do 1 over 2, 1 over 2?
Yeah,
But,
you could, absolutely. I'm just factoring everything out.
okay.
So here, just as a reminder, 1 over the square root of 2 here is C1 and C2. Right? That's what this is. So the idea is that if it works for one set, if it works for each one, it works for the sum of them. And that's always true. Okay.
My other question was when,
Yeah.
when you're adding them, I thought it was had to be like plus minus, or is that like completely unrelated?
Well, there's two options. So there's a plus combination and a minus combination. I could pick either one I want. In the problem set, I pick generically plus or minus, so you evaluate both of them.
I think, okay.
Either one is perfectly okay. Yeah, so I can certainly write plus or minus here. Again, there's no difference between plus or minus, right? They're still both linear operators, minus and plus. Except minus, if you flip it, then it's anti-symmetric, right? X minus y is minus y minus x, right? So there's a little bit of a subtlety there, but it's the same idea. We can make this a plus or a minus. Okay, you said you had a second question. What, that was it? Okay. All right, so just let's just look at a couple of very simple operators, all right? And then next class on Monday, we'll do some practice. Okay. All right, because some of these will look very strange, very strange, and we'll have to kind of think about them, and we'll have a way to a prescription to start thinking about these operators. So some common operators for functions, wave functions. I'm just going to write down a couple, and we'll finish it up on Monday. Common measurement operators. And on Monday, we'll talk about how to use them. I just want to give you these operators. All right, so I'm just going to make a quick table. So we're going to think about the observable that we want to measure. And I'll make a symbol for that observable. And then the operator. All right, well, the first thing that we want to look at, of course, is position. Right, and the symbol that we use for position is X or Y or Z, whatever you prefer. It depends on the system. And the operator, again, every time we write an operator, we put a little hat on top of it. The operator for position is just X. Now that sounds really weird. But as we'll see, if you want to measure the position of an electron, all you need to do is take its wave function and add an X to the outside of it and do an integral. So you just need to plug in an X. We'll look at those techniques in a little bit, our next class. All right, you just need to add an X to your equation. So you're going to have X times the wave function, and that will give you some information about the position. Very strange operation, but it gets weirder. I just want to do two more. Another one is momentum. Remember, classically, momentum is a vector, which I call P, which is the mass of the object times its velocity. It's the quantity that's conserved in space. And momentum, let's say along the x direction, right? So this is the x direction of momentum. Because momentum is a vector, it's got multiple components, is minus I. This number h bar, we'll have to come up with the h bar. What the hell is that? D by, and it's times the derivative. So the momentum has something to do with the derivative with respect to position. Very strange. All right, so we'll define this number next time. H bar is a special constant that we'll define next time. So very strangely, position is a real number. Of course, it should be a real number, right? It's right here. But for some reason, in this perspective, momentum is a complex number. Very strange. Right? We'll have to explore that a little more carefully. Why is it complex? All right, we're out of time, so we'll just leave it there for now, and we'll come up and start thinking about these two operators are the most important ones in this class. Because when we can combine these two, and we'll see, we'll get energy, right? And that'll be really important for us, energy. But we'll have to explore why we get a negative sign here and an I and this H bar. What the hell are all these things? Okay, so we'll look at that next time. Right? But really, you know, we have to do some derivatives. All right, so we'll look at that later. Have a good weekend, guys.
You should go green next. So you go from hot pink to green. I just wanted to. She starts off with like. I don't want to leave it. I mean, they're all done good before.